and reduction, interesting chemistry, and some acronyms that we can learn here to help us. It says here oxidation reduction reactions. We're still talking about reactions in aqueous solutions. And the first example that's shown here comes straight out of our textbook. It's not a reaction that's shown in an aqueous solution, but what this is actually a piece of magnesium metal. It's kind of hard to tell from the picture, but this is actually magnesium metal. And all they've done, the scientist or student, all they've done is they take a piece of magnesium metal, and you can do this at your house. They subjected it to a flame, like even just a flame from a match or a lighter, and eventually the magnesium will catch on fire and it will burn. So it's undergoing what's called a combustion reaction. But a combustion reaction, and if you're thinking, well, what about the internal combustion reactions? Is that the same kind of thing? Yeah, any kind of combustion reaction is also known as an oxidation reduction reaction. We also call them electron transfer reactions. And I'm going to start off tonight's lecture with a little acronym, and that is OIL rig. And I'm sure that some of you know this acronym. OIL stands for oxidation. So oxidation is losing electrons. So we're talking about electrons because it's an electron transfer process. And rig stands for reduction. So reduction is gaining electrons. So oxidation is losing electrons and reduction is gaining electrons. And again, you can't have oxidation without reduction. You can't have reduction without oxidation. They are going to happen at the same time. The overall reaction of what's happening here in this picture right here is this. I'm going to rewrite this, and it's on the slide, but it bears rewriting. So what's actually happening is the student is taking a piece of magnesium. Magnesium is just a solid metal. They're combining it with oxygen. And if you're wondering, like, how are they combining it with the oxygen? Well, what's happening is when magnesium undergoes combustion, combustion takes place in what? In the air, right? I'm sure that everybody's smothered a fire before, whether it's, maybe a candle or a small fire, If a fire doesn't have oxygen, it's not going to burn. So the combustion process occurs in the presence of oxygen. So the magnesium is combining with the oxygen, and you're forming magnesium oxide, MgO. So we'll balance that out like that. And that's the formula shown right here, okay? Magnesium combining with oxygen to give you magnesium oxide. And again, that's the combustion of magnesium. But again, as I've told you, combustion is an oxidation reduction reaction. Oftentimes we call these redox reactions for short, okay, redox reactions. Anyhow, if we examine what are called the half reactions, what that means is if we just focus in on what's happening with the magnesium. Okay, so let's just talk about the magnesium. Well, the magnesium is just pure magnesium here, right? So it's got no charge, right? If you touch a piece of magnesium metal, you're not going to get a shock from it. It doesn't have any kind of charge. However, when magnesium is found in magnesium oxide, you know this from nomenclature that magnesium is an alkaline earth. It's got a charge of 2+, and oxide is 2-, and that's why they combine MgO to make magnesium oxide. So you're going from magnesium, just plain old magnesium with no charge, and you're forming a magnesium 2+ ion. Now, since you have two magnesium 2+ ions, that means that in order to balance that out, since we have 2 times a +2 here, that would mean +4. Well, if there's 0 charge over here, what would I have to add to balance that out? And the answer is 4 electrons, because electrons are negative, right? So I form a +4 charge total from my magnesium. So I have to balance that out with 4 electrons, okay? Remember, electrons are negative. +4 plus -4 gives you 0. If we look at what's happening with the oxygen, well, the oxygen is starting out just plain old oxygen from the atmosphere. It has no charge. But we're ending up with 2 oxides, right? An oxide has a -2 charge. So if we have 2 times -2, that would give us overall -4 on that side. So how do we balance out -4? Well, in order for that to happen, we'd have to add -4 over here. And we're adding 4 electrons because electrons are negative. So we call these half reactions. What's happening in each one? If we just examine the reaction with magnesium only, again, this is just a half reaction. It's only half of the story, but it's going to help us understand what the heck is going on here. It says this is an oxidation half reaction, loses electrons, right? If we go back to oil, oxidation is losing electrons. The magnesium is losing electrons to form magnesium 2 plus. The second reaction, the second half reaction, oxygen plus 4 electrons gives you 2 oxides. This is a reduction half reaction. Why? Because reduction is gaining, right? The oxygen is gaining electrons. And here's the really fascinating part. If you tally up those two reactions, okay, if you add those two reactions together, and we'll cancel anything that's the same on opposite sides. Notice what's the same on opposite sides is the 4 electrons. Those cancel out. So in my reactants, I'm left over with 2 magnesium plus oxygen produces 2 magnesium 2 plus 2 oxygen 2 minus, and those combine to give you 2 moles of magnesium oxide. So that's an oxidation reduction reaction or a redox reaction. Again, the important thing that you know, or there's many important things here, you have to know that oxidation is losing electrons, reduction is gaining electrons. You can't have one without the other. And if you tally up the two half reactions, the oxidation half reaction and the reduction half reaction, you should get the overall reaction of the entire oxidation reduction process like that. Okay? Now, if you need to look at some other examples, this is another example of an oxidation reduction reaction. It might be a little bit difficult, but I'll try to blow it up here. So let's see what's happening. It says the zinc bar, so this is nothing more than just a pure bar of zinc, which is a solid, okay? And it says it's in an aqueous solution of copper 2 sulfate. So this is copper 2 sulfate, and it's aqueous, of course. Okay, so what the heck is happening here? What's happening is spontaneously, the zinc is losing 2 electrons, right? You see that this part right here, that represents the zinc metal. And the zinc is actually losing electrons. The solid zinc is losing electrons. It's transferring them to the copper. Why? Because copper sulfate is made from copper 2 plus and a sulfate anion. So as the zinc loses the 2 electrons, right, it ends up becoming Zn 2 plus the 2 electrons that it lost. The 2 electrons combine with the copper to make copper solid. So that is what you see forming over here. So then you're going to have the zinc ions in solution, and you actually see the copper as a solid depositing onto the zinc bar here. So if you're like, oh, it just looks like kind of ugly here. Well, that's what that is. That's copper coming out of the solution. And that just happens spontaneously. So what's the oxidation? The zinc is being oxidized. So we could write that over here to summarize. Zinc is being oxidized like this. We have zinc solid, which is losing electrons, right? Oxidation is losing. So we get zinc 2 plus ion, that's aqueous, and we end up with 2 electrons. The copper is being reduced, right? Reduction is gaining electrons. We're starting it with copper 2 plus ions, and they're gaining 2 electrons to form copper solid like that. So if I tally both of these up, you can see that the 2 electrons are the same on opposite sides. And so the overall redox process is zinc in the solid phase plus copper 2 plus in the aqueous phase produces, and I'm running out of space here, zinc 2 plus in the aqueous phase plus solid copper. Now you might be wondering, where did the sulfate anion go, Mr. Dion? Well, that's a spectator ion, so we're leaving it out of the overall reduction or a redox process. This example over here shows a little bit different experiment. Again, these are experiments that maybe some of you might have done in high school, or maybe you've never seen them before, but they're inexpensive reactions to try. They're really good because, you know, when students begin starting the study of chemistry, they like to do reactions where you can see something with the naked eye. It's very easy to see what's going on here. Let's take a look at this side over here. Okay, so I'm going to kind of break up the slides in two pieces here. Okay, in the first beaker here, it says, when a piece of copper wire, so that's what this is here, it's just a piece of copper wire, it doesn't cost too much, is placed in an aqueous solution of silver nitrate. So again, this is copper wire here, and it's in a solution of AgNO3, and that's an aqueous solution. What happens is that the copper ends up becoming oxidized, right? Oxidation is losing. You start with solid copper, right here, that's solid copper, all this is solid. It ends up losing electrons to become copper 2+ ions. Where do those electrons go? They combine with silver ions to make solid silver. So if you're wondering, hey, Mr. Dion, all these like little crystals on this thing over here, is that silver? Yeah, absolutely it is. That is actually silver crystallizing or solidifying on top of what was the copper wire. Okay, I'm not going to go over each half reaction in this case, but the same thing is occurring here. The copper is being oxidized, it's losing electrons, and the silver is gaining electrons, and the nitrate is a spectator ion. Give me a thumbs up if you follow me, at least on the concept. Just the concept of oxidation reduction. We're going to look at it in a little more detail here, but even if you're with me, part of the way. All right, great, wonderful. Well, let's take a look at this overall reaction here. Now, this is, again, what's going on in this first picture here, but, sometimes it helps to look at everything in the form of an equation. So we have our solid zinc in our copper 2 sulfate solution, and we end up with zinc sulfate and copper solid, okay? Now remember that the copper in copper sulfate is copper 2+, right? Because the sulfate is 2-, and the zinc in zinc sulfate is zinc 2+, because the sulfate is 2-. Now again, when we look at the half reactions, we leave the sulfate out overall because it's a spectator ion. Now we've gone over this in some detail already, but I want to cover one more thing, and that's what a reducing agent is and what an oxidizing agent is. So follow me carefully here in terms of just the terminology. Okay, now we've already discussed this. We said that if zinc is losing electrons to form a zinc 2+ ion, it's being oxidized, right? Nothing new there. Oxidation is losing electrons. Well, since the zinc is causing the copper 2+ to be reduced, we call the zinc a reducing agent. So not only is zinc being oxidized, we call it an agent, and we would call it a reducing agent. It's not being reduced, it's causing the reduction. Okay, maybe we could put that in brackets here. It is causing reduction. Okay, and I'm sure that most of you are, get this right off the bat, but I just want to be 100% sure here. Now, if we look at the copper 2+, the copper 2+ is gaining electrons. It's being reduced, right? Reduction. Let me do a different color here. Pick the blue. Reduction is gaining. Nothing new there. So we have our copper 2+ gaining 2 electrons. We get copper solid. So the copper is reduced, right? Everybody knows that. However, we can call the copper 2+ an oxidizing agent. It's not being oxidized, but it's causing the oxidation of zinc. Okay. All right. So we'll say it is causing oxidation. Okay. So you can see how these, whenever I look at this slide, all I can think of is, this lends itself to a multiple choice question really easily. All I have to do is put up any kind of redox reaction and say, what's the oxidizing agent? What's the reducing agent? Who's being oxidized? Who's being reduced, right? They can make a question up. I can write a question for these really quickly. So, and if you're thinking, well, that's easy, all I have to be able to do is identify what's being oxidized and what's reduced, understand what a reducing agent and an oxidizing agent are, and I'll be as sound as the pound. Absolutely. Absolutely. Well, before we get into redox in even more detail, and I think we look at redox again, it comes up a little bit later in the course. But I want to talk about oxidation numbers for a second, okay? Now, if you're like, what the heck's an oxidation number, Mr. Dion? Well, we've already looked at a few this evening. Say, for example, we're just looking at this reaction that we've talked about for the last 10 minutes, okay? Now, the zinc, if I just have pure zinc metal, I told you, it's got no charge. So we actually call that zinc 0. So you'd say the oxidation number of the zinc is 0. And if you're thinking, well, the oxidation number of the zinc over here, it can't be 0. It's got a charge. It's 2+. Exactly. So you'd say that the oxidation number of the zinc over here, you'd say it's +2. Okay? The oxidation number of copper 2+ is +2. The oxidation number of solid copper would be 0. Well, what about And here's where it gets way more interesting. What about sulfate? The sulfate 2 minus. And you're like, oh, I thought you were going to forget about that. It's a spectator ion. No, it's important. What's the oxidation number of the oxygen, and what's the oxidation number of the sulfur in here? Right? It's 2 minus overall for everything, but what are the individual oxidation numbers for the sulfur and the oxygen? Well, the short answer is that there's a whole set of rules that you have to learn and able to be, in order to be able to assign oxidation numbers to elements in polyatomic ions or molecules. And we're going to look at those rules right now. You can see I got 2 whole pages of them, and then we'll try some examples. So see if you can follow me on these. And these are rules that you're responsible for knowing. Oxidation number. Okay, the first one is the charge the atom would have in a molecule or an ionic compound if electrons were completely transferred. So that's really what oxidation number is. Okay, like say for example, if we go back to our, ionic, I'll pick something even simpler, NaCl, right? Sodium chloride. Well, you know that the sodium is +1 and the chloride is -1, right? Because the sodium gives up an electron to the chlorine. Okay, so the oxidation number of the sodium would be +1 and that of chloride would be -1. All right, so let's get into the nitty-gritty of the rules. Number 2, this is probably the easiest, one of the easier rules, okay? Free elements in their uncombined state have an oxidation number of 0. So that means when you have a plain old element by itself, all alone, it's got a number of 0. Pretty easy, huh? The only caveat to that is you have to remember the diatomic elements, okay? Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and hydrogen. We went over that in the nomenclature section in my videos. Phosphorus comes in a packet of 4, for example. Sulfur sometimes comes in a packet of 8. But whenever you have an element by itself, it's got an oxidation number of 0. Okay? Let me give you another example. Say you had gold, Au, just some solid gold. It's got an oxidation number of 0. Okay? All right. Next, it says a monatomic ion. So that's an ion made up of one element. The oxidation number is equal to the charge on the ion. And if you're thinking, hey, this isn't too bad because I know that all the alkali metals, everything in group 1A, will take on a charge of +1. Absolutely. So that means that all ions from group 1A will be +1. Anything from group 2 would be +2. The transition metals gets a little bit trickier, but if you see iron 3+, well, then it means it's got an oxidation number of +3. If you have O2-, it's got an oxidation number of -2, so on and so forth. Okay. The next one is a good one that you have to memorize, and this is 99% of the time. The oxidation number of oxygen is almost always -2. There are very few exceptions to this rule. One notable exception would be hydrogen peroxide. If you're wondering, hey, do I have to know that rule? Yeah, you got to know that rule. Okay, you got to know that in hydrogen peroxide, oxygen has an oxidation state of 1, but that's, I think, probably the only exception. There might be some exceptions in the practice problems that I gave, but very few exceptions to that. So oxygen's almost always -2. See, my numbers aren't, don't line up 100% here, but anyhow. So next it says the oxidation number of hydrogen is +1, except when it's bonded to a metal in a binary compound. In these cases, its oxidation number is -1. So to summarize this one, hydrogen is almost always +1, except for when it's combined with a metal. Let me give you an example. If you have H2O, for example, right, the oxidation number of oxygen, it says it's almost always -2. So if I have -2 and I have 2 hydrogens, well, each of these must be +1 because +1 times 2 gives you +2. +2 plus -2 gives you 0, right? So we just figured out the oxidation numbers of hydrogen and oxygen and water. However, let's say you had sodium hydride. Okay, so here you have hydrogen combined with a metal. And we know that since sodium is in group 1A, it's +1. Well, in this case, hydrogen would be -1. Okay, rule number 5, group 1A metals are +1, group 2A metals are +2, and fluorine, this is a great rule, fluorine never changes, okay? It's like death and taxes. It's always -1, okay? No exceptions to the fluorine rule. You just saw me invoke the next rule. The sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge of the molecule or ion. So if you're wondering, how did you figure this out, Mr. Dion? Well, Water by itself, if I just have H2O, we don't write H2O plus. No, that's not a thing. We don't write H2O minus. That's not a thing either. Water doesn't have a charge overall. So what I was doing here is if oxygen is almost always -2, that means I have one oxygen. Overall, the charge of water is 0. So -2 plus something equals 0. That something must be +2. And if I have 2 hydrogens, +2 divided by 2 gives me +1. And that's how I figured out that the charge on the hydrogen, or its oxidation number, is +1. All right. And the last one says oxidation numbers do not have to be integers. The number, the oxidation number of oxygen in the superoxide ion, O2 minus, is 1/2. Now, an example of that would be this. If you have KO2, that's potassium superoxide. We won't see that a ton. Again, I might put that in practice problems or something, but since potassium is in group 1A, it's got a charge of +1, so this must be -1, and since you got 2 of them, it equals -1/2, right? Each oxygen is -1/2. Anyhow, with all those rules in mind, okay, and I don't expect you to have them all memorized in 10 seconds, but I hope that you would have read the book before coming to class and given it the old college try. Let's take a look at some examples. The first one is lithium oxide, and it says, assign the oxidation numbers to all the elements in the following compounds and ions. So we've got lithium oxide. So we've got Li2O. Could anybody tell me what the oxidation number of the oxygen is? Or the lithium? Just spit it out or type it in the chat, whichever one you think you might know. And there's no tricks here. All right, so the lithium is in group 1A, so it's a group 1A metal. So therefore, it's going to have an oxidation number of +1. And the oxygen is almost always -2, very few exceptions. This wouldn't be one of them, so the oxidation number of the oxygen is -2. Does that work out? We have -2, we'd have -2 plus 2 times +1, and that would equal 0. Perfect. Okay, the next one's a little trickier. We got HNO3. And the only way for you to be able to solve this one, HNO3, is for you to know your polyatomic ions. Okay, let me walk you through this one a little bit. You've got HNO3, and you know that comes from a proton and the nitrate ion, right? You know that it's simply a proton combined with a nitrate. So that means that the oxidation number of the hydrogen is +1. Now we've got the nitrate ion to unpack. Okay, how are we going to do that? Well, let's rewrite it over here. We've got the nitrate ion. Okay, now we know that the overall charge of this polyatomic ion is -1. We know that oxygen is almost always -2. There are 3 oxygens, so -2 times 3 gives me -6. Now, -6 plus something, I'll call it x, equals -1, right? Because the overall charge of my polyatomic ion, my nitrate, is -1. So what would x be equal to? X would be equal to +5. So that means that my nitrogen is +5, and my oxygen is not -6, it's -2. So I have -2 for my oxygen, +5 for my nitrogen, and +1 for my proton. So here are the answers: +5, -2, and +1. For the first one, it was +1 and -2. Well, with that in mind, I want you to try this polyatomic ion here. Could anybody tell me the name of this polyatomic ion? It's one of the ones you have to have memorized in this class. I'll give you a few seconds to think about it. Come up with an answer. Yeah, thanks, Kristen. It's the dichromate ion. That's 100% correct. I'll write it down here. Dichromate. All right. Does anybody have an oxidation number for the chromium and the oxygen and dichromate? Okay, yeah, we got -2 and +6. That sounds reasonable. So let's start with the oxygen. Oxygen is almost always -2. I have 7 of those. That would give me -14. The overall charge of my polyatomic ion is -2. So 14 plus x equals -2. What must my x equal? X must equal, sorry, -14 plus x equals -2. So what was my x must equal? 12. But I've got 2 over here, right? I've got to have a total of +12 over here. But +12 divided by 2 gives me +6, doesn't it? So that means that each one of the chromium ions is +6, and the oxygens are each -2. So +6 for the chromium and -2 for the oxygen. Give me a thumbs up if you're like, I think I get it. You're even part of the way with me. All right. Okay, great. Not a simple concept, but definitely something that we need to know in this class, okay? Being able to assign oxidation numbers. These are the oxidation numbers of elements in their compounds. And you notice that some of them are really simple. And I don't like to use the word simple in chemistry class, but you notice that almost everything in group 1A, almost everything is +1. You know, there's the exception here of the hydride that we saw. Almost everything in group 2A is +2. If you go to group 3A, you get a lot of +3s. Once you get down here, it gets more interesting. Okay, but also you see the fluorine is always -1. You see there's nothing for the noble gases because they don't like to gain or lose electrons. But you notice that over here, they get way more complex when you get into the transition metals. You have a whole holy host of oxidation numbers over here. And so let's say you had something like this. Let's say you had Fe2O3. Well, if you look at iron, okay, if you look at iron, you see that iron can either be +3 or +2. And if you're wondering, well, how the hell am I going to figure out which one it is? Well, let's look at an example. The example will always be something you'll be able to figure it out. Okay, I'm not going to give you anything that's impossible to do. So if I want to figure out if this iron is +2 or +3, I start working with my oxygen. The oxygen is -2. There's 3 of them. That gives me -6. Now the overall charge of Fe2O3 is 0, so that means -6 plus something equals 0. So that means that x is equal to +6. I have +6 here, but there's 2 iron, right, divided by 2, so that means that the iron is actually +3. So this is why this is called iron 3 oxide, right? Because I determined that the charge on the iron is +3, and I already know that the charge on my oxygen is -2. Okay, so there's always a way to determine oxidation number. Just also, you know, it's going to move on, but I just can't help but share this with you. If you look at some of these elements, you probably notice that some of them, like, whoa, Mr. Dion, it's getting out of hand here. Look at all the oxidation numbers for nitrogen. Well, I can tell you right now that this figure doesn't even show anywhere near the whole story, okay? Carbon can be +4, +3, +2, +1, 0, -1, -2, -3, -4. So many of these elements have even more oxidation numbers. So they get more complicated. But again, the rules that I've given you this evening will give you all the necessary tools to determine the oxidation number of any element in any compound or ion that we're going to see in this class. Okay? Well, let's switch gears and talk about solution stoichiometry. So we're really kind of switching modes here for a second. We went from redox reactions, and then we looked at oxidation numbers, and we covered the rules of oxidation numbers, right? Because in order for you to be able to assign who's being oxidized, who's being reduced, who's the reducing agent, who's an oxidizing agent, in order for you to be able to do that, you've got to be able to assign oxidation numbers. But now we're going to switch to something not completely different. We're still talking about solutions, but we're going to talk about solution stoichiometry. Okay? Now, solution stoichiometry, it says here the concentration of a solution is the amount of solute present in a given quantity of solvent or solution. Now, everybody here, you or any friend that you have is aware of what concentration is. Even if, it might not be something you think about in terms of numbers, you think about coffee, right? I don't know if any of you are coffee drinkers, but I like to have coffee. And, sometimes I'll go over to somebody's house, my mother-in-law maybe, and she'll make me a cup of coffee, and it's so weak, I'll say, I tell my wife, like, if she makes this any stronger, it might wake somebody up, So what am I talking about? I'm saying the coffee is not concentrated enough for my liking, right? But then you might go over to another friend's, and they make it way too concentrated. So you're used, people are used to the word concentration in their everyday life. When I was a child, we used to make Kool-Aid up in Canada, and you put the Kool-Aid crystals in the water. And, it had a recipe, but we would never follow that. We'd basically add the crystals until they couldn't dissolve anymore. We made a saturated solution. So it was really concentrated, right? So even in our everyday language, we're used to using concentrated and describing concentrations, okay? But in the same definition holds true, right? It's the amount of Kool-Aid. It's the amount of coffee dissolved in the amount of water. Now, again, we're talking about aqueous solutions here. So our solvent in this chapter is, I think, almost all the time going to be water is our solvent. And what's our solute? That's going to be some kind of compound that we're dissolving, whether it's a covalent compound or an ionic compound. But we're concerned with really getting into the numbers associated with concentration. And the way that we define concentration in chemistry is using molarity. And for molarity, we use big M. So it's got to be an uppercase. I'll write that in here. It's an uppercase M. Uppercase, okay? And molarity, which describes the concentration of a solution in its in a numerical form, is the moles of our solute. We've looked at how to calculate moles already in this class, divided by the liters of solution. So it's just the number of moles divided by liters. So you're going to see me use that conversion a lot. The molarity is equal to moles per liter. That's something you've got to be 100% aware of. You need to have this in your head moving forward. Well, let's take a look here. It says preparing a solution of known concentration. Probably not going to ask you a million questions about how to prepare solutions. But here's, you have a scientist making a solution in some kind of a volumetric flask. And if you're in Group A, we talked about volumetric flasks in the first lab, I believe. And tonight, if you're in Group B, we'll probably talk about them a little bit more. But in a volumetric flask, there's only one line, right? There's only one gradation on the entire thing. And if you wanted to make a solution with a known concentration, the reason why a volumetric flask is so handy is because it has a very precise marking showing the volume of solution. Now, if you weighed out your solid and you knew the mass of that solid, right, you can take the mass in grams, you can divide it by the molar mass in grams per mole, and that will give you the number of moles. So that would give you the number of moles, okay? And then if you know this volume in liters, okay, so this is our volume, then our molarity, or our concentration, is going to be the number of moles per liter, right? The number of moles divided by volume, sometimes we call it like that. Anyhow, so what you would do is you'd weigh out your solid, you put it in the volumetric flask, and then you dilute it up to the meniscus, you'd shake it or something. Now here's my Drake meme that I threw in a few semesters ago. The problem with this first one here is it shows them dumping a solid directly into a volumetric flask. That's actually a big no-no, and this is in our textbook, I believe. I wouldn't do that. I wouldn't throw a solid directly into a volumetric. What you would want to do is you'd weigh it out and you would dissolve it in the solvent, and then you'd pour that solution in, and then you would dilute that. That's the way to do a proper, what's called a quantitative transfer. Anyhow, I'm probably not going to quiz you a whole hell of a lot on quantitative transfer, but I just want you to be aware of this kind of a little mistake here. I would not prepare a solution that way. That would be a no-no. Anyhow, well, with that in mind, let's see if we can apply our newfound knowledge to solve a problem. This is the exact kind of problem you could expect to see on your next exam, which is when? February 25th. So coming up, it says how many grams of potassium dichromate are required to prepare a 250 ml solution whose concentration is 2.16 molar, right? Which is the same as 2.16 moles per liter. Well, we can start by using our formula that molarity is equal to the number of moles per liter. We're given our molarity and we're given our volume. Right? Another way to write this is to say, and I should have shown you this again, is we say molarity is equal to N over V. So N is equal to the number of moles, and V is obviously equal to volume. So we could say, okay, well, I've got M and I've got V. I can solve for M, right? I can rearrange that and I can say the number of moles of potassium dichromate is equal to the molarity times the volume. Let's put in some numbers here. I have 2.16 molar, which is moles per liter. And I'm going to multiply that by my volume, which is 250 milliliters. Now I'm going to do the conversion up here. I have 250 milliliters. Could anybody tell me how many milliliters there are in 1 liter? Milli in 1 liter? It's not a trick. Mr. Dion's not a big fan of the trick. Yeah, there's 1,000. So I have 1,000 milliliters in 1 liter. You can see that milliliters cancel out like that, and we get that our volume in liters is equal to 0.250 liters. So we'll put that in here, 0.250 liters, like that. You can see that the volume in liters cancels out, and we're left over with, grab my calculator here. You should always bring a calculator to chemistry class, right? 2.16 times 0.25, and we end up with 0.54 moles, okay, of potassium dichromate. But they're asking us how many grams of potassium dichromate are required. Well, we have the number of moles. We can go to the periodic table and we can calculate the molar mass of potassium dichromate, can't we? We add up the mass of 2 potassiums, 2 chromiums, 7 oxygens. And when you do that, you end up with 294.185. I have way too many sig figs, but whatever. Grams per mole. All right. In fact, I should have put an extra sig fig here, shouldn't I? There we go, 0.540 moles. So now we have the number of moles and we have the molar mass. So if we want to find out the mass of our potassium dichromate, so we'll say mass of K2Cr2O7 is going to be equal to the number of moles, 0.540 moles, multiplied by 294.185 grams per mole. Moles cancel, and we're left over with 4 times. Am I the only person who punches things in their calculator incorrectly? I think I might be. All right, here we go. So we get 85.8. All right, here we go. 85.8 grams. Oops, did I make a mistake here? So let me double check my math here. Oh, I must have punched it into my calculator incorrectly. Sorry about that. Can you guys double check my math here for me? If anybody's got a calculator, if you take 0.54, I don't know what I did the first time, times 294.185. Yeah, it's 159 grams. I was like, that's not right. 159 grams of potassium dichromate. All right. Oops, where did I go there? Right here. Give me a thumbs up if you follow me on that one. You're with me on determining the number of grams in the number of grams of solute in the 250 mils of 2.16 molar potassium dichromate. So I like to solve problems most of the time without looking at my notes, and I just looked over here at my notes, and I noticed that I did this entire problem using dimensional analysis just in one fell swoop. If you want to do the problem that way, there's no problem at all. I find that when you're teaching these kind of problems right here, it's kind of best to do it as a two-step process. But if you did it in one, in one whole step, and if you're like, what do you mean by one step? If you said, okay, well, I'm starting with 0.250 liters of my solution, and I have 2.16 moles per liter, like that. And then I have 294.185 grams of solute in 1 mole of solute. You can see that that obviously works, there's nothing wrong with that at all, and you would end up with 159 grams. But again, I found that teaching this over the years, it's kind of better to do it as a two-step process when you're learning it. Anyhow, it seems like most of you are following me. So let's try another one. It says, in a biochemical assay, a chemist needs to add 3.81 grams of glucose to a reaction mixture. Calculate the volume in milliliters of a 2.53 molar glucose solution she should use for the addition. Okay, so you're adding 3.18 grams of glucose, but you're not measuring it on a balance, right? You're not weighing out 3.81 grams of solid glucose. You're putting that 3.81 grams in by using this solution here. So I want everybody to give this one a try, and the only bit of information that I need to give you is the molar mass of glucose. We're going to use 180 decimal, so 3.6 grams per mole. I'm going to give you 2 minutes to give this one a try. I'll go grab a drink of water. Okay. Did anybody get an answer for this one? Maybe I didn't give you enough time. Does anybody have an answer? I'll give you another second. Okay, well, anyhow, let's give it the old college try here. We can solve this by dimensional analysis. Starting with, we know that we want to add 3.81 grams of glucose, so we'll call that GLUC, like that. And we know that in 1 mole of glucose, we have 180 grams of glucose. If we were to stop right here, just using this conversion factor, we would have the number of moles of glucose, wouldn't we? Now, how are we going to go from moles of glucose to milliliters? Well, luckily, we have the concentration in moles per liter, so we can use that as a conversion factor, right? We know that we have 2.53 moles of glucose in 1 liter of the glucose solution. And if I was to stop here, you see moles of glucose cancel. If I was to stop here, I'd have liters of glucose, but we want milliliters of glucose. And so we're going to multiply that by 1 liter has 1,000 milliliters, like that. So we have liters canceling out, and we end up with the milliliters of our glucose solution. And I'm going to double check my math here. So 3.81 divided by 180 by 3 times 1,000, and you should end up with 8.37 milliliters. 8.37 milliliters. So again, what the scientist would do, what she would do is she would go and she would take 8.37 milliliters from this solution, and by doing that, she is adding exactly 3.81 grams of glucose, although it's in solution. Give me a thumbs up if you follow me on that one. I keep switching slides here. Accident. Anybody follow me on that one? It's in the same vein as 4.7. Okay, great. Thanks, Branson. Thanks, Kristen. Good. Anthony. All right, perfect. Well, let's move on from there and let's talk about dilution. Before we get too far on this one, I just want to throw it out there that the formula that we're going to look at on this slide, which you can see at the bottom here, probably one of the most loved formulas by students in this class. There's nothing wrong with the formula at all. I just want to caution you that, you got to be careful as to when you want to use it. So it says dilution is the procedure for preparing a less concentrated solution from a more concentrated solution. You think about everyday life, if you buy orange juice from concentrate in the can, okay, it's smaller in a little can of orange juice concentrate, right? Orange. It's easier, it's cheaper to transport because it takes up less space. But then you take it and you dilute it in a pitcher, right? And you can make a big old jug of orange drink, from your orange juice from concentrate, right? So that's a dilution. Now, the reason we do dilution, to be honest, most of the time in chemistry is because scientists will usually buy solutions of acids or bases that are more concentrated, and then they'll dilute them as they need them, okay? And the reason why is for the same reason. They don't want to transport these huge volumes of water for nothing. We can get water from a tap, or we can get distilled water from a distilled water tap. So dilution is just adding solvent is all you're doing. You can see the number of moles of the solute doesn't change, but the volume does. So the formula for dilution, or the relationship between concentration and volume, I should say, is this. The initial concentration times the initial volume is going to be equal to the final concentration times the final volume. Right? Now, if you think about it, if you have moles or moles per liter multiplied by liter, right? Molar is moles per liter, volume is liters. So all you're saying is the number of moles, the initial number of moles is going to be equal to the final number of moles, right? And obviously you can see that in the two beakers here. The number of moles of particles and the number of particles doesn't change. Okay, so that's the dilution formula there. And next, I think I have a problem where we use the dilution formula. It says, describe how you would prepare a 500 milliliter, how you would prepare 500 milliliters of a 1.75 molar sulfuric acid solution, starting with 8.61 molar stock solution. So you purchase this probably from some kind of chemical supplier. You buy 8.61 molar, it's pretty concentrated, and you only want to have, something that's about a quarter, a little less than a quarter concentrated. So what the heck would you do? You're going to use the formula M1 times V1 is equal to M2 times V2. We have our V2, don't we? This is the volume that we want to end up with. Okay. We have our M2. This is the concentration we want to end up with. We're trying to make 500 mils of this concentration. And we have our M1, right? But we want to know how much of the stock solution we should measure out in order to make that new solution with or 1.75 molar solution in half a liter of it, right? 500 milliliters. So we're going to isolate V1. When we do that, we get V1 is equal to M2 times V2 divided by M1. We just plug in our numbers. We have our M2, which is 1.75 molar. We're going to multiply that by our V2, which is 500 milliliters. And we're going to divide that by our molarity, which is of our stock solution, which is 8.61 molar, like that. You see that molarity cancels, moles per liter cancel. We're left over with milliliters. And when you punch that spinach into your calculator, you get 1.75 times 500 divided by 8.61, and you end up with 102 milliliters as being your volume. So what you would have to do is you would have to measure out 102 milliliters of the stock solution, and then you would dilute it up in a 500 ml volumetric, right, to the 500 milliliter mark. So you'd start out with your 102 mils, and then you're just going to dilute it with water all the way up to the top, like that. That's the procedure. Now, I made a note here to myself, and it says here, a student pointed out to me one time, why can you use milliliters in here if the units of molarity are moles per liter? Don't you want your units to be consistent? Well, it wouldn't matter if you were to do 1.75 molar multiplied by 0.500 liters divided by 8.61 molar, like that, right? You're still going to end up with the right answer, but now you'd end up with the answer in liters instead of milliliters, right? You'd end up with 0.102 liters, but then you'd have to convert that to milliliters. You'd have to multiply by 1,000 milliliters per liter. So by leaving milliliters in here, you're perfectly safe, and you can skip a step, right? You don't have to do an extra calculation for nothing there. All right. Getting pretty close to the end here. Okay, let's take a look at one more concept, and then we'll probably call it a day. We'll take a look at gravimetric analysis. Gravimetric analysis is usually worth the value of maybe one multiple choice question in an entire exam. It's a technique that can be used to determine the amount of an unknown ion in some kind of substance. All right, you got to kind of, and I think the easiest way to understand what the heck gravimetric analysis is to look at a problem. So let's go ahead first and just read this problem, and then we're going to go back to the steps, okay? So here's the kind of problem that you'd see in gravimetric analysis. I'm really unorthodox here, right? Reading a problem before we even study the concept. But trust me, it helps. It says, if you start out with about 0.5 gram of some kind of ionic compound that contains chloride ions in an unknown metal, okay? So we have something that's got X metal and then chloride ions, and we don't know the identity of X, okay? We dissolve it in water, okay? And then we treat it with silver nitrate, right? And then we end up with silver chloride, okay? What is the percent by mass of chloride in the original sample? So if we end up forming silver chloride, right, the silver chloride is going to be formed from the silver and the chloride that was in the original compound. So we can determine the mass of chloride in here, and then we can divide that by the mass that we started with, and we can determine the percent by mass of chloride in the original compound. So the steps are shown here of what gravimetric analysis is. So you take that unknown substance and you dissolve it in water. But when it says unknown substance, we'll say cation, in this example that we're looking at, cation unknown, okay, anion known. So basically, it's not completely unknown. You only don't know the cation. It says you react the unknown substance and you form a precipitate, right? You filter off, you dry the precipitate, you weigh it, and then you use the chemical formula of the new substance that you formed from the known substance and the known anion, and then you're able to determine the amount of the unknown ion. Okay? If you're still not 100% sure with me, trust me, I've taught this enough that the best way to do it is to look at a problem. So watch carefully, and we'll see if we can figure out what the heck is going on here, and then we'll call it a night. But let's take a look, and I'm going to write out the formula of what, or the reaction of what the heck is happening. So as I told you, we have some kind of ionic compound that has X, the unknown cation, and we're combining that. I should put aqueous by that. It's a solution, and we're combining that with silver nitrate, which is aqueous, okay? And then what are we ending up with? We're ending up with silver chloride. Silver chloride is insoluble. And then we're ending up with XNO3. So again, the unknown is the X, but we know everything else. All right. Now, it tells me that I'm ending up with this much silver chloride. So the first thing I'm going to do is I want to determine the percent of chloride in silver chloride, and then I can multiply that by this mass to determine the mass of chlorine. Watch. So if I want to figure out the mass, percent mass of chlorine in silver chloride, that's going to be equal to the molar mass of chlorine. I'm just looking at the periodic table. It's 35.45 grams per mole divided by the molar mass of silver chloride. Molar mass of silver chloride, AgCl, is equal to, I got 143.4 grams per mole. So 143.4 grams per mole. And then I'm going to multiply all that by 100. Okay, you see that the units of grams per mole cancel. And I get that the percentage of chlorine or chloride in silver chloride is 24.72. So 24.72% chlorine. Well, in my 1.0882 grams, I know that 24.72% of that is chloride. Okay, so I can say that 1.0882 grams multiplied by 0.2472, all I did was divide this by 100 because it's a percentage, is equal to 0.2690 grams of chlorine in the silver chloride. All right, so that's the mass of my silver chloride. Okay, that's the total mass of chloride, because if I end up with 0.2690 grams of chloride here, that means I had 0.2690 grams of chloride to start out with. Right? It's a balanced equation. I didn't destroy any matter, and I don't create any matter. So finally, if I want to know the percent, it's asking us what's the percent by mass chloride in the original compound. The percent mass chloride in XCl is going to be equal to 0.2690 grams in the total, which was 0.5662 grams. I multiply that by 100%, and I end up with 47.51% chlorine in XCl. So that's how much chloride was in there from the beginning. All right, so that's one problem that deals with gravimetric analysis. The next subject that we're going to look at is titrations, but I think it's worth waiting for our next lecture to look at titrations, because it takes a little bit of thought to understand the concept of titrations.